Today's topic will be the residue at infinity. So in order to explain this concept, let us consider an analytic function, and we just simply specified what kind of analytic function. Suppose f of z is an analytic function such that the set of all its singular points is bounded. So let's emphasize this, is bounded. Bounded. So let's start making a picture. So maybe here I will divide the board into the two parts. So this will be writing on the left, and the picture will be on the. So we have here the singularity. So maybe use the red color. Singularities of the function f of z. So we have here one point, another. Those singularities don't need to be isolated, so I can make a cluster of those singularities. You see, this is cluster of singularities. So those are all singular points, maybe. Okay. Yeah, that's. And now, what we do, we just simply assume and let C be a contour. Let's say like this, simple, closed contour, positively oriented, of course, containing all the singular points, all these singular points in the domain, in the area, in the domain, bounded by C. So, okay, so there it is. So here we have the contour. So this is my contour. That's my contour. And all singular points are inside. So this is my C. They are all inside this contour. Okay, so now, of course, what is our task? We will compute the question, okay, or maybe put it like clearly, let's say the problem. Compute, and here we have here integral C f of z dz. So the idea here is relatively simple. Maybe it is appropriate to understand, let's say, to explain that since the contour C contains all the singular points inside, so clearly the function f of z has no singularities outside C, no singularities. And if it's no singularities, so by the fact that C and the singularities are bounded, we can always choose. So suppose here we have here the coordinate, maybe that's not nice, coordinate system. So we have here the not here, I put it here. You have the origin is here. I am always able to find a large disk of large radius, say R, still ugly, So this is R, the disk of radius R, such that the whole picture is contained inside this disk. Everything is inside. The contours is inside. The singularities are inside. And let's denote this disk CR because that's a circle of the radius R. So the boundary of this disk is CR. And now you look here. The function is analytic in the region in between these two contours. So you have the contour C and contour CR, and of course, look, the function f of z is analytic in between. So we can now just simply use the facts. So let's write it down. By Cauchy theorem, we have that this integral C f of z dz is equal, and I can change the contour C to the CR, to the green one, and the same function, the dz. And now we will do a couple of changes. Namely, first, why not to apply a change of variable? So change of variable. So if you do this change of variables, so of course dz becomes minus 1 over w squared, and this will be dw. And what happens to the contour? Contour is actually transformed to the how? So let's see how this change of variables means simply w is equal 1 to z is changing the contour. So now let's see what happens here. So we have here our contour CR. This is our contour CR. And now apply this. So what is the CR? CR, let me write it down. CR is basically parameterized by the z of t is equal r. This is EIT. So what will be w? So w of t will be equal 1 over r e minus it. You just simply remember that. This will be the, this is like, let's say, that's the parameterization. You plug it in. So w of t is equal 1 r e I t, and that's parameterization. Where the contour is, so this contour is here. So it is going that way. So this was a large circle, so this is small circle. But it goes other direction. You see, this is the minus here, which shows you the direction is changed. So in such a case, I can continue writing my integral. So this will be equal, and I have here integral by after change of variables. So this is change of variables, and I'm having here the integral, and now I have here the C1 over R. But notice that's not necessary, so that must be minus because this is opposite orientation. The orientation is changed. This is minus, so I write it down. This is minus C R because they will go into the other, not positive but negative orientation. And then we have here 1 f, and z becomes 1 over w, 1 over w, and dz becomes minus 1. This is w squared dw. And of course, you can now reverse the orientation of the circle. Let's reverse it. So we put here CR, and then you have two minuses. This is one minus and another minus. They cancel each other. So we are getting here, this is 1, this is 1 w, 1 over w squared dw. And now, of course, who tells you you need to use this w, because let's say too many symbols is always tiring, so we just return, so put it like this, 1 over r, and return to my 1 over z. Yeah, why not? I call it again z. It's convenient. Just simply remember. So now what happens here? All the singularities were inside. So the outside goes here. Look, clearly. That's important. Outside goes here. So this is the points of regular points of z, which were all outside this circle. This outside, this part goes inside the circle, excluding origin. So that means here's everything goes inside, and there are no singular points except one of them, namely the origin, the 0. So 0 can be a singular point. So this is the singular point. So we can notice here that the function, put it clearly, the function, and I put here f 1 over z squared has only one singular point. Inside C1 over R. Inside C1 over R. And this is point exactly z0 equals 0. So now we can say, okay, in this case I know what is the answer. This will be just simply residue of that function at that singular point. 1 over z squared, put here 0, and we forgot, of course, something very important. Of course you notice, right? 2 pi I, and now the residue of f1 over z times 1 over z squared at 0. So, as you notice, we are switching from one function to another function. So in this case, we notice that in this case we're just simply trying to get the result of this particular integral in such a way that basically we get all the residues. Let's say, okay, all these values of inside, just with one shot, we compute the one residue at 0 of this particular function. So in this case, we can write it down. We have here the function f of z, and now we associate with this function, so put it like this, the function looks like this, g of z, and that one is equal to f1 of z, and this was 1 over z squared. In order for it, if you look carefully, if you have this integral, you may have many residues of this function, because all of them, possibly many of them, are inside the contour C. But now you have reduced the computations of all these residues at those points to one single point, the origin, z0. You compute this residue and you get immediately the value of the whole integral. So of course that requires some attention. This is kind of a big simplification, so we will introduce this as a definition. So put it like that. Definition. Suppose the set of singular points of the analytic function f of z is again bounded, then we will say A, that, then we say that, and we say that f of z has an isolated singularity at infinity. At infinity, and the type of the singularity, this singularity, will be the type of the zero singularity for the function g of z. So the singularity will be the same as the singularity, as the type of singularity at 0 for the function g of z equals f1 over z times 1 over z squared. So the type, so you look at that function, you say, oh, it's a pole, oh, it's a removable singular. But it is not exactly f1 over z, it's also multiplied, so it has to be emphasized, it is also multiplied by this particular factor. So that means we have also c, 10, we put, and let me put it in red, that we have here, this will be r residue of f of z at infinity. It will be by the definition, the residue of this function g, so this will be f 1 over z times 1 over z squared at 0, and we will call it the residue at infinity of f of z. Yeah, that's basically the whole idea. So as you notice, we have here new concepts, so we need to make a couple of examples just to get used to this new concept, to this new idea. So example number 1. And let's say, for a given function f of z, determine the type of its singularity at infinity, and if it is isolated, compute residue at infinity. So put it like this, residue of f of z at infinity. Okay, so let's start A. My first example will be f of z equals 1, and I put here z to the power 3 minus z to the power 8. Okay, so first of all, we notice that singular points, what are singular points of the function f of z? So those are the points, we can write it down, this is z cubed, and this is 1 minus z5, and here we make a little picture. This is my picture, and then this is my point 1, and then you have 1, 1, 1, 1, 1, unit circle. So we have the roots of this equation, So this is, so z to the 5 is equal to 1, so we have here those roots, you have a pentagon, you remember pentagon. We computed those roots, we exactly know where they are. So they are finitely many. And of course, 0 of that function is here. So the function f of z has 6 singular points, and they are finite, so definitely they are bounded. They are inside, you see they are inside any large circle, so they are bounded. So that means simply conclusion, infinity is an isolated singular point of f of z. So that's an isolated singular point. So now we can compute with the classification of the type of the singularity. So let's write it down. G of z, write it again, this is f and this is 1 over z times 1 over z squared, and rewrite it down. So what do I get here? I'm getting here this is equal to, let's write it down, 1 divided by 1 over z cubed minus 1 over z 8, and this is 1 over z squared. Yes, remember there's always additional term. Now we can simplify it. And that's what we are getting here simply is, okay, maybe I simplify it, and you just check if I'm right. So this will be z to the power 5 minus 1, and I'm getting this particular expression. So you notice here that 0 is not, z0 is not a singular point. Basically, you notice here that z0 is removable singularity of g of z. So in such a case, we are obtaining immediately conclusion z0 equals 0, sorry, maybe infinity is removable singularity of f of z. Removable. Very good. So if it's removable, so I don't need to compute the residue, because in this case you immediately recognize that for removable in singularity it is always 0, and we are done. So we are done with this example. So let me go to another example. Let's try another one. So example B. So this will be B. The same question. So let's call it like f of z is equal to, and that one will be 1 divided by sine 1 over z. So clearly you have here two types of singularity. First of all, z0 equals to 0. Why? Because you cannot divide, so that means it prevents you. For this formula has no value for z equals 0. That means you cannot, you have clearly exclusion of the z0 equals 0 from the domain. So that's one. And the second one you have here, and you have to understand that probably every 0, zk, so zk must be the 0 of sine 1 over z. So that means, what does it mean? Maybe let's write it down. Solve the equation. Sine of z is equal to 0. Gives you other singular points. There will be all poles, because as you remember, if you have an analytic function in the denominator, 0 of the denominator is always a pole. So what does it mean? That means 1 over, put here like this, zk is equal pi k. K has to be equal plus minus 1 plus minus 2. 0 is excluded. Why? You cannot divide by 0, right? Because zk in such a case, it is equal to 1 over pi k, it's excluded. And now you see, wow, that means this is the bounded set of singularities. This is a bounded set of singularities. Okay, let's make a picture. Let's see what's happening here. So here we have here the complex plane. Then we just got that one is my point 0. That's my singular point. And then of course I have here singularity. So start with k equal 1. So where is k is equal 1? So this will be 1 over pi. And then of course there will be another side minus 1 over pi. And then I have here k equal 2. So just in the middle, this will be 1 over 2 pi. And that one is minus 1 over 2 pi. And then 1/3, 1/4 of, let's say, pi of these values, and you are getting whole sequence, infinitely many singular points. They all converge to 0. So you see the set. So this is the set of singular points of f of z is infinite, but still bounded. And you can easily notice that they are all contained in the unit ball, okay? Unit ball, like a unit circle, inside the unit circle. Bounded. So that means conclusion. Infinity is an isolated singularity of f of z. Very good. So let's compute the residue. So in this case, we have this function g of z, and we write again, this will be 1 over z, and here we have here times 1 over z squared. So what does it give me? So it gives you, this is sine of z times 1 over z squared. And you could do it two ways, as this is the clearly, but you can see here that clearly this is so maybe you should recognize it. So let's say like this. Z0 is equal 0 is a pole of order 3. How do I get this order 3? I know this is 1, and for sine is 1. 0 is of order 1, 0 of order 1. So 1 plus 2 is 3. And you could use the formula. You could use the formula for the computations, but it will involve, as you will notice by practicing, that this formula that provides you the possibility to compute the residue of the poles of order m in general is not very friendly, as long as there is a kind of the necessity to compute the limits involved with these derivatives. So here we will have the limit. So maybe let's write down this formula maybe. So what is the formula? Let me write it down. So we have here that this residue of g of z at 0 will be equal. So this is order 3, so this will be 1 over here. Then you have here limit z goes to 0. and then you have to take the second derivative dz square, and then you take your function g and multiply by z cubed, so that means this will be z divided by sine of z. And after computing the second derivative, you can figure it out what kind of a limit it is. It may not be very simple, but there is always another way, and we are going to use the another way. This way was already explained in my previous lecture. So this is the way, just simply, that we can try to figure it out what is the coefficients a minus 1 by looking at the power series expansions of the function sine. So let me do it. So in such a case, notice, so we have here g of z, and we are looking for the coefficient which is a minus 1. So let's write it down, a minus 1. That's your residue. This is your residue. This is your residue. So let me continue. So I have here 1 divided by sine of z. And now I will just simply write it down here. What is sine? Power series expansion. So it starts with z, then you have here z cubed divided by 3 factorial plus z5 divided by 5 factorial minus blah 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 blah. I don't really care about the higher degrees. And then I go and I do this simplification. First of all, I pull out the z. So I'm getting here 1, and I pull out the z. So I put it like this. This is z, and then I'm getting 1 minus z squared 3 factorial plus z4 5 factorial minus. Oh, and then I get that one here. Yes, and this shows me, yes, indeed, this is the pole of order 3. Why? Because the function that stands here, 1 minus, and I can pull the z squared here, it is 1 divided by 3 factorial, and this will be, minus, and this will be z squared divided by 5 factorial, plus, is analytic. If you put here 0, it's analytic. So this is analytic function. So the pole is order 3. So pole of order 3. Indeed. So it's just a confirmation that what we did. And then you look at this expression and you say, that's my q. So I'm having here 1 minus q is equal, n is equal 0 to infinity qn. So I can rewrite the whole expression using the power series. So let me rewrite it now. So that one is equal z squared, and here I'm getting 1 plus z squared 1 3 factorial minus z squared, and this one is 5 factorial plus, and then you have another one, z to the power 4 1 3 factorial. This is my q, this will be my q squared, and then you have here minus, and this will be z squared 5 factorial plus, and then other terms. And I need the power standing by the 1 over z. So maybe put it. I need the power. Sorry, I need the coefficient standing by the power 1 over z. This is my residue. But look, I cannot have such a coefficient. Those are all even. And this is even. And this one is also even. But that one is odd. So it's impossible. It's impossible to find such a coefficient. There is no such coefficient. If there is no such coefficient here, that means it's 0. And then we can just simply write it. Conclusion. This residue of f of z at infinity, which is the same as the residue of this function g of z at 0 is 0, because there is no such a coefficient. So we are done. This is 0. So this is my second example. It is maybe appropriate to... Is it enough space? Well, I think so. It's enough. Okay, so do another example. So put it number C. So take the function f of z is equal, and this will be, take z to the power n, and this will be sine 1 over z. So n is a natural number, so that means either 1, 2, 3, or etc. But we do not specify it. So now we want to compute it. So how to compute it? So again, so you can see that from the previous question, we have actually here, you already know that z0 is equal to 0 is the only singular point. So it's isolated, and in this case, you also know that this only singular point is essential singularity. And why it is essential singularity? Yeah, because we know the Lorentz series expansion. So let me write it down. F of z is equal to z to the power n sine 1 of z. And now we can expand it. So we are getting z to the power n, and then I have here again, so this starts 1 over z. Then you have here Lorentz series, so this goes like this, 1 over 3 factorial z to the power 3 plus 1 over 5 factorial z to the power 5 plus, and then let me write it down. This will be 1 over k factorial, 2k plus 1 factorial z to the power 2k plus 1. And infinity many. So what will be the residue? Residue is the coefficient. So a minus 1, standing by the power a minus 1. So that means if n is here, so if n is here, this power is 2. So let me check it. Let me write it down, this power. So we have here Zn, which stands here, and take the general terms here. So what will be the power if I multiply these two things, these two terms? I'm getting this is 2n plus 1. So I'm getting this will be Zn minus 2n minus 1. And I know this must be equal to the power minus 1. So you are getting that n minus n minus 1 minus n minus 1 must be equal to 1. And that implies immediately, sorry, this is k. Let me write it down. Sorry, k plus 1. So this is equal z. I write it down differently. I prefer to write it down like this, 1. And this will be z2k minus n plus 1. So this must be the power, you see, so it will be standing by the z. So that must be equal to 1. So that means 2k minus n plus 1 is, okay, so it's 1. So that means 2k must be equal to n. And that explains. You can see immediately that if n, therefore if n is even, if n is odd, then what do I get? I get 0. That means a minus 1 must be equal to 0, because even number cannot be equal to odd number. So if n is odd, so maybe let me write down the answer. So we are getting here the answer, write it down, residue, and I put here again the function. The function is Zn, and this will be sine 1 over z at infinity will be equal, and we just obtained this is 0 if n is odd. If n is odd. But if n is even, if n is equal to m, then that means k is equal to m, then this residue will be equal minus 1 to the power m divided by 2m plus 1 factorial. And we computed this residue in two cases, so we got it. So let me continue, and it is actually now appropriate to go to a different type of example. So this will be example number 2, and we'll say the following. So for a given function f of z and the contour c, compute the integral c f of z dz. So okay, let's start my first example A. So we have here integral c, and I put here dz, and this will be en. Surprise, surprise, I make it complicated. That guy is having a lots of singular points. No, lots of singular points, a lot, infinitely many. So where c is equal, just a unit circle, so this will be z is equal to 1. Okay, so let's find the singularities. Singularities. So solution. Let's find the singularities. So z0 equals to 0, definitely a singular point. Why? You cannot divide by 0. And then you can see that the poles, those will be all poles because they are 0 of the analytic function. That's an analytic function. You look at the zeros of this analytic function, zeros. So we can solve this equation. This is Ez is equal to 1. And then you see that this is equivalent, that 1 over z must be equal to pi I. So maybe put it like this. First ki, and k is equal. And I have to exclude 0 again. This is plus minus 1, plus minus 2, etc. So that means those are the poles which are equal. This will be 1 divided by 2 pi ki. I can put this I at the top, change it to minus, and those are my points. Or maybe, let me see, keep it, okay, keep it in the bottom. Okay, keep it in the bottom. That's okay. So there's all infinite number of poles. So those are poles, and you can easily verify by taking derivatives of order 1. So they are all definitely, let's say, simple. So let me make a picture where these points are. So now we have to make a picture, and let's make a small coordinate system. And now here, this is my first singular point here, 0, 0, and then we have here k is equal to 1. So I'm getting here, so this will be like this will be 1i divided by 2 pi. And then it will be on the opposite side, it will be minus I divided by 2 pi. Then you have here I divided by 4 pi. And then you have here I divided by minus 4 pi, and then there's many other, and they all converge to 0. So you can notice f of z has infinitely many singularities, all of them except 0 are isolated. Yeah, it's isolated. You can always take a little, that's isolated. Oh, I'm isolating it. Yeah. So you can see also that, and they are bounded. Clearly. Wow, I showed it, bounded. Took any disk sufficiently large, contains them all. Okay, good. So we can actually apply the residue at infinity. So let's write it down. Therefore, we have, and let me continue. I put it like this, integral, and this is c, and this is dz, and this one e1 over z minus 1 equals, this will be 2 pi I, never forget it, and this will be residue of that function, 1 e1 over z minus 1 at infinity, which gives me 2 pi I residue, and let's do it. So this will be 1, this will be ez minus 1 times 1 over z squared, good, at 0. And let's compute this residue. So let me write it down, my g of z, that's how I like to denote it. So this will be this function here. This is my function g of z. So this function is equal, and pull this first. And then you have here ez, and this is minus 1. And I have to figure it out. Is it a pole? Yes, it is a pole of order actually 3. And let's do it the way that we practice to do it. So this is z squared by taking the expansion of this function here, e. So what is this function? So this one is equal to 1. Then you have here plus z divided by 1 factorial plus z squared plus 2 factorial plus z3 divided by 3 factorial plus, and then you put here minus 1, and then you get cancellation, and you pull this z out. Just do it like that, and you are getting, this is z cubed. Pole of order 3. And that one will be cancelled, so you are getting 1, which is this one. This term becomes 1. And then you have here plus, and this will be z like that. It's easier to write it down. So this will be over 2 factorial, and that one is plus z 3 factorial plus, and so on. So now you look at this expression as the sum. So this will be 1 plus q. This is my q. So denote this one q. So you're getting 1 divided by 1 plus q. So that everything becomes n is equal 0 to infinity. This will be minus 1 to the power n q to the power n. And you can rewrite it, and so that one is equal 1 over z cubed. And here I'm getting 1 plus q. So first q is here. Then you have q, then you have q squared, then you have qn. But here, remember, maybe I don't. This is minus, because this is minus 1, so I should correct myself. So this will be minus q plus q square, etc. Minus, etc. So let me correct it and then write it minus. Sorry, minus, and this will be z, and this is 1 like that, plus z q plus, and then you have plus, and then you will have z square, and this will be 1 factorial plus z plus 3 factorial plus also square, and then you have minus again. This is z cubed 1 2 factorial plus z 3 factorial cube and plus. So now I'm looking for the a minus 1, which stands by the power z at the bottom in the denominator. So I look at the where it is. So if this is 3, so I'm looking for the power 2, and you can immediately recognize that I need to have the z square in this expansion here. Z square. So where is z square? This is giving me, this is one z, this is another z, so it's all together is z square. So I'm getting here minus and that one. So this will be minus 1 divided by 3 factorial. So put it like this. A minus 1 is equal, and the first one gives me minus 1 over 3 factorial, which is here. And then I say, oh, I have another one, z squared. But don't forget, here is another square. Another square. So this is plus, so put here plus, and then you have here that guy. Here, that guy. So it will be 1 over 2, and you have to take it square. Okay, still not good. Like this. No. Like this. Why does writing like square? Okay. So that's coming from here. And then you simplify it. This is minus 1/6, and this is plus 1/4. So this one is equal to minus 2 plus 3, 12 is equal 1, 12, and we can write the answer. The integral over c dz is equal, so this is e1 over z minus 1 d, minus 1 is equal to 2 pi I times the residue, which is computed here, 1 over 12. We obtain this is pi I over 6, and we are done. So that's the example of the computations, and mainly this is the I would say like this, it's sufficient number of the integral. We could do a couple of more, but maybe you can, maybe we'll do another one, but which is one moment. I think I have one. Let me look into the text and find some kind of a no. So let me continue in a moment, in the second part. Okay, thank you. For a moment, we take a